Coaxial cable is a cable where you have, this is a coaxial cable, and I wish I could zoom in. The camera I'm using isn't very good at zooming in, but there's a wire right here at the center. You've used coaxial cables before. There's a wire at the center, and along that same axis as the wire is this other outer wire that's a cylindrical hollow cylinder. Now they don't just put air there; they put some type of an insulating material so that it's easy. You can bend it around. You don't have to worry about the wire, the center wire, and the cylindrical wire touching one another. So I can bend this all I want, and they're never going to touch one another. Okay. Now I want to show you then what happens in the physics of a coaxial cable. With a coaxial cable, you might have something that looks like this. You have a wire going like that, and then on the same axis of that, we're going to make this long. So I'm drawing this all has the same radius. So that's a radius capital R, we'll say. And then this is a wire that's going through the center. So this is metal, and that's a metal piece of wire. And so I just want to show you something that, and let's say that whatever material's in here, let's say that it's that mu for that material is equal to mu naught. And let's also say that the current going this way, I, is equal to the currents coming down, the current coming down the sides of this. So we'll say current coming down the sides is also I. Okay? So if there's 1 amp going up this way, there's 1 amp coming down. And that's usually the case because this is like going into some appliance. And you can think of the appliance as being a junction. And the junction rule says that the current going into a junction is equal to the current coming out of a junction. So, whatever it's going into, we should expect the same current going in as coming out, or you're charging that whatever that appliance is. It's gaining charge. Okay, so I'm going to first find the field in here. The field in here, just draw an Amperian loop, doing this in 3 dimensions at this point. And so that's just going to be, when you do all this, it's going to be going real fast. It's mu naught I through the Amperian loop times the closed loop integral of B dot dl. And so it's just the 1I that's in there. So it's mu naught times I is equal to, now you can get rid of, since the B's are circulating this way, but so are the dl's. So you can get rid of the dot product. And then you can pull the B out because it should be the same at every point in here. Remember, the only I that matters is the I through the Amperian membrane. So none of this outer I is going through there. And so you have mu naught I is equal to, when you pull the B out, you can add all the dl's up and you're going to get B 2 pi R. Okay, so the I, or the B rather, is going to be equal to mu naught I over 2 pi R. Okay, but that's not the interesting thing. The interesting thing is that when I put the field, when I want to know the field out here, and I put my Amperian loop out here, like so, that Amperian loop, if you think about it, it has no current, no net current through it. We'll count the current going one way as positive, the current coming down the other way as negative. And so I'm going to have mu naught for out here, mu naught times 0 is equal to the closed loop integral of B dot dl. And so the point is that the B out here is going to be 0. And so what that means is that when you use a coaxial cable, you don't have to worry about even though you have all this current running through here, you don't have to worry about it making magnetic fields outside of it. The magnetic field outside of a coaxial cable a lot of times is 0.